So, welcome everyone to today's row. It's my great pleasure to introduce today's speaker, Bahar Taskesen. Bahar is an assistant professor of operation management at the University of Chicago Booth School of Business. She completed a PhD at EPFL in Switzerland in 2024, and she actually graduated with in the group of Daniel Kuhn. So it's a great pleasure to have you here, Bahar. Without further ado, I want to give the control of the screen and the mic to you.
Thank you so much. Thanks for this kind introduction and also inviting me to present here. I mean, also this series is very special for me because when I had I did my first presentation as a PhD student in this series. So when it was COVID times. So thank you so much. Thanks for inviting me. And now I'm going to talk about distribution robust linear quadratic control. And this is a joint work with Danny Yanku, Chelko Cheat, and Daniel Kuhn. So, oops, okay. So the problem that I'm going to talk about has several applications, and then its importance, the way that I talk about is linear quadratic control problem, can be hardly overstated, basically. For example, it was used in navigation systems for Apollo missions and was critical for the success of the first moon landing. Since then, linear quadratic Gaussian control is routinely used in robotics, electrical engineering, chemical engineering, and many other engineering fields. It's even used in treatment for neurological disorders, gait control in Parkinson's disease, and so on and so forth. So the problem that we're going to talk about, as we will see, has several applications. So what we are planning now today is that I'm going to first introduce you the problem, linear quadratic control problems. Actually, let me see if I can manage to show my cursor, but okay, well, cannot. So, and we will see that this problem is affected by uncertainty that is typically modeled by a random variable. And oftentimes, we actually do not know the underlying distribution of these random variables. Therefore, we will focus on robust version of that problem to see if we can actually, as a controller, get prepared for a worst case distribution. And next, we will establish some structure results for this problem that will enable us to design efficient algorithms to solve it. So, and finally, we will talk about these numerical solution methods. Okay, so this is our overall agenda. So let's see. Now we're gonna first introduce you. I'm gonna introduce you to the linear quadratic control problem. We are looking at a linear dynamical system in discrete time. Okay, so the next state, denoted by xt plus 1, is a linear function of state at time t, control input at time t, and some exogenous noise wt. So the objective of the control problem is to find a sequence of control inputs that minimizes the expected value of a convex quadratic cost function. This objective function incentivizes the controller to derive the state close to 0, such that x transpose qx is small, without spending much energy, such that u transpose ru is small. Okay, so this is the objective of the controller. And what happens is that oftentimes, actually, we do not have the exact measurement of x, which is our state. What happens is that we actually only observe, we only have access to some measurements denoted by outputs yt. And these are usually the way that in the problem that we're looking at is linear transformation of the current state corrupted with some measurement noise. Okay, so therefore now realistically, if you want to design a controller, what we want is that this controller should be a measurable function of all the outputs observed up to time t. It may not depend on the feature at time t. So that's one thing. And as we can only observe the outputs yt, it should be a measurable function of these outputs. Okay. So now I will also assume that true. So the exogenous uncertainties in this presentation, actually throughout the presentation, will be denoted by red notation, and we assume that these are these are mutually independent and have zero mean under this distribution P. Okay, we will see that some of these assumptions could be relaxed in the end, but let's assume that for the moment. Okay. So now I would like to introduce you some compact formulation of this previous problem to write it in a nice compact form because we're going to call this problem a lot of times. And So now let's rewrite the classical linear quadratic Gaussian control problem more compactly by introducing some new notation. So this is our objective function, right, that we just seen before. And we're going to introduce some stack vectors that combine the stack's inputs of all time periods and also the control inputs at all time periods. And we can actually introduce new symbols for this objective and write this quadratic form more compactly by using these stack vectors and block diagonal matrices, calligraphic Q and R. Okay, so it's exactly the same objective. By using a similar technique, what we can need to do is we can write down this, state transition equations as a one single giant state equation, right? So this is actually the same recursion that we have seen before, but now we're going to introduce these new symbols for these big matrices that we are saying, block matrices. And what we can actually do is we can write it in this form by using the stack vector notation. Next, similarly, what we can actually do is we can also write down the measurement equations by using the stack vector notation. And y is just, in this case, is going to be linear function of this x multiplied by this calligraphic c that we introduced and added by this measurement noise stack vector v. Okay, when we design the controller, so this is our objective and these are our constraints. When we're designing an objective, right, control, we are interested in the controllers that are causal with respect to outputs y, and this set is denoted by calligraphic ui for the moment, okay? So the controller's objective is to solve this optimization problem, right? Okay. So now what we know about this problem is something very, very nice, actually. So for any distribution P that satisfies these assumptions that we have seen before, mean zero and mutually independent, the classical linear quadratic control problem can be addressed by dynamic programming techniques, and optimal solution actually admits an elegant solution. What we actually see is the separation of estimation and control. To be more precise, the feedback gain matrix KT can be computed independently of the underlying distribution P by using dynamic programming. And the state estimation, which is the expectation of xt given all the outputs observations that we have, though in the most general form, is actually nonlinear in what all the condition variables y0 to yt, and we show that actually it's sharply hard to compute it when the underlying distribution is in the most general form. Okay, what we've seen that this has many applications. Of course, if we make some assumptions about the underlying distribution, this problem is still very efficiently solvable. That is, when the underlying distribution P is actually Gaussian, then what we know is that this state estimator is actually linear in the outputs y0 to yt, and it can be efficiently computed using Kalman filtering. So basically, when we change the distribution, this KT matrix is still the same, right? How we compute this is dynamic programming and independent of the underlying distribution P. Basically, then we can solve this problem very efficiently using dynamic programming and Kalman filtering. And hence, all the applications that we have seen actually were realized because of it's also very, we can actually solve this problem very efficiently. Okay, so now, unfortunately, the linear quadratic control problem that we have seen before becomes intractable, right? If the noise variables are not Gaussian, which is quite a limitation, right? And this limits is actual practical usefulness. And also, the noise distributions are actually not even known in most practical applications. Therefore, this actually prompts us to study distribution robust version of this linear quadratic Gaussian control problem. Okay, so therefore now I formally state here our distributionally robust linear quadratic control problem, where the goal of the controller is to minimize worst case expected cost across all distributions of the exogenous uncertainties in some ambiguity set script W. So therefore, there's a zero-sum game between the controller and a nature who is trying to find a distribution that is going to be undesirable for the controller. Okay. So now obviously this set W contains all the distributions for the feasible distributions for the nature to choose in an adversarial fashion. Now perhaps the question is like, how do we define this W, which should be defined in all the probability distribution space, right? So for that, we're going to actually use optimal transport. And well, this is something I also work on separately. So I thought it would be also maybe a nice moment to talk about it. And then also we will see how we're going to use this to define this ambiguous set W, script W for the adversary. Okay. So optimal transport problem is introduced in the 18th century by French mathematician Gaspard Monge, and it is motivated by the problem of relocating materials like earth or minerals to construct structures at another place. So many people were interested in this problem, and then thanks to contributions of many mathematicians, geometricians, and then all the engineers and so on, now today we are using it effectively to compare two distributions. Okay. And it essentially seeks the most efficient way of transforming distribution P1, for example, that we see on the left, into P2 in an analogy to reshaping one pile of sand into another. Well, to be able to do that, we should give the cost of moving one unit mass from one point to another, which is in this case, if these two locations are xi1 and xi2, then is denoted by cost of xi1 and xi2. And this C is often referred to as transportation distance. So in 1942, Nobel laureate Leonid Kantorovich formulated the optimal transport problem as we see here, which aims to find the cheapest transportation plan pi for morphing distribution P1 into P2. So this distribution plans pi's are actually nothing but joint distribution of xi1 and xi2 with marginals P1 and P2. So let me quickly illustrate it in a very small, simple example. Therefore, if we are looking at this one-dimensional random variables, then actually if we define this pi in this form, then if we were to integrate pi along xi1, then we should have distribution P2. And if we were to integrate pi along xi2, then we would have the distribution P1. Okay. So basically, this problem also attracted many people to work on it because this is a very nice problem. First of all, it's always feasible, right? We can always find a transportation plan pi that's going to be feasible, which is the joint independent distribution of xi1 and xi2 with marginals P1 and P2. And when the cost is lower semi-continuous and bounded below, then this problem is guaranteed to be solvable. So, well, the question is like, how do we compute it? Because this itself is an optimization problem, right? When these two distributions, that P1 and P2 are discrete distributions, then we can write this optimization problem that is equivalent to computing optimal transport problem as a tractable linear program. But when one of the distributions is not discrete and is generic, then this problem in fact becomes immediately very hard. In fact, so just a bit side note, that if you want to compute optimal transport between a continuous distribution and a discrete distribution, it is sharply hard already in the simplest imaginable setting. That is when P1 is a uniform distribution on the unit hypercube, and when P2 is a discrete distribution with two atoms. So therefore, with very little hope to solve this problem in polynomial time if one of the distributions is actually generic. So I spare the details of the proof here, but basically at its core, for the people that might be interested in it, it relies on reducing the computation of optimal transport problem between a two-point distribution and a uniform distribution over the unit hypercube to computation of volume of knapsack polytope, which is already known to be very sharply hard to solve. Okay. Okay. So basically, this result says, well, this problem is hard to solve, but what we know about this problem, and this fact was given very early on, is that if these two distributions are Gaussian distributions, let's say that they have zero means and covariance is sigma 1, sigma 2 respectively, then Wasserstein distance, or I mean, the way that we write it is like now Wasserstein distance, but it's in fact a special case of optimal transport, is actually given by analytical formula that we see here. And it only depends on the covariance matrices of these two distributions. That is quite nice, good news. And in 1990, a closely related corollary has been shown that actually, if these P1 and P2 are not Gaussian distributions, but they are generic, but then the same analytic formula that we have seen before provides a lower bound on the optimal transport distance between P1 and P2. So now this is going to come up later in our present in this talk, that I will refer to this lower bound as Galbraith distance between covariance matrices sigma 1 and sigma 2. Okay? Okay, so let's keep this in mind. And what we're going to do is we're going to use optimal transport to define this feasible set for the adversary, which is W. We're going to put a bit more structure on it, okay? We will assume that W can be expressed as a product of separate ambiguity sets for different exogenous uncertainties. This means that the exogenous uncertainties are mutually independent under every possible distribution in W. And to give an example about how we're going to construct it, let's go over one of these ambiguity sets in detail. So the ambiguity set associated with the initial state x0 is defined as the family of all zero mean distributions of x0 with a two Wasserstein ball around some given nominal distribution p hat x0. And the other ambiguity sets are also constructed in the similar fashion. So now you might gonna ask, okay, well, that VC is like a ball in the probability space for each exogenous exogenous uncertainty that we have. But then you might gonna ask, what are these actually nominal distributions, right? Because these seem to be critical in our modeling. Well, we're going to set them to Gaussian with mean 0, and perhaps this is a reasonable assumption, because now if we set the radiuses, this Rx0, Rwt, and Rv2 to 0, we effectively find ourselves by solving a classical linear quadratic Gaussian control problem if these are Gaussian distributions, right? And we know that this is only tractable for Gaussian distributions. So therefore, if the nominal distributions are not 0, we would indeed have actually very little hope to solve this problem, because already when this hyperparameters, the radius is equal to 0, we find ourselves in this intractable case. Though I want to emphasize one thing. So even though the centers are Gaussian distributions, actually these balls also contain non-Gaussian distributions, right? So it's just their centers are Gaussian distributions. Okay. So now, before talking about this, like actually how hard this min-max problem would be, or how do we hope to solve it, I would like to talk to you like that an inherent complexity that comes from the way that the information structure in the problem that we are looking at. So let's look at traditional linear quadratic control problem, right? So we are trying to solve this optimization problem as a controller. There's some cyclic dependencies in this problem. Basically, there is some decision-dependent information structure. So to see this, let's quickly create a diagram. So measured outputs y impacts input u, because u is a causal function of these outputs, right? And then the inputs, on the other hand, are impact the states through the state equations. Okay, well, then the states goes back and impact the outputs. Well, therefore, we are facing with some chicken and egg problem, because the information available to the controller depends on previous control decisions. And what we know of about such problems where the controller has decision-dependent information are usually extremely difficult. Okay. On top of that, we also have another player in this game, which is the adversary. So we look at min-max problem. And actually, when we look at this problem as its whole, we might have very little hope to solve it. And now what we're going to see is that this problem, because it's such a structured problem, and then the way that we construct ambiguity sets W in this fashion that we see, is going to admit a very, very, very nice structure form that will allow us to design some algorithms actually to solve it very effectively. Okay, even though it looks quite horrible. Okay. So the technique that I'm going to talk about is the convexification technique for classical linear quadratic Gaussian control problem. It's a reparametrization of the classical problem, and this is known as purified outputs, and it's introduced by Bantal, Boyd, and Nemirovsky in their landmark paper in 2005. Okay, so now what happens is that we look at our original system that has these dynamics, then we actually copy our original system and simply we delete the noise from that system. So it's like a simulation, right? So we start from x at 0 is equal to 0, for example. Then we know this H and C matrices because we know the system identification matrices of this linear dynamical system. And we just compute this x hat and y hat through this simulation, small simulation, okay? So then purified outputs are actually defined in this form. They're denoted by eta, and they're constructed by taking the difference between the outputs of the original system and the noise-free system. So these outputs are useful for two reasons. So first of all, they're exogenous. So they do not depend, they provide the exact same information as the original outputs. And the exogenous part could be actually shown that it's very easy to by just looking at these equations. It's quite easy to show it. And what we also know is that the controller is actually indifferent between seeing these purified outputs and actual outputs y. That is, the family of all causal output feedback policies actually match exactly the family of all causal purified output feedback policies. In other words, the controller should be indifferent between observing y and eta. Then what we can actually simply do is we can look at this cycle that we have, ask controller to design controls that are causal in eta. Therefore, we will replace this outputs with purified outputs. The controllers will be causal in purified outputs. Well, the purified outputs only dependent on exogenous uncertainties W and V. Therefore, what happens is that this cycle that we have is actually broken. Okay. And therefore now what we can actually do is we can look at our optimization problem. Instead of looking at the controllers that are causal in Y, we look at the controllers that are causal in, purified outputs eta. And we also can remove this equations for Y. And we can actually try to aim to solve this problem that we see here before, which is a convex optimization problem now. So another thing that I want you to remember is that if you remember in the classical setting, the state estimations, the optimal controller is linear in the state estimation. State estimation is linear in the outputs that we are conditioning on. Therefore, actually, the optimal controller in the classical linear quadratic Gaussian control problem is in fact in this form, right? So U star should be a linear function of y, and U capital star here should be a lower triangular block matrix, right? Because we are interested in causal controllers, right? It may not depend on the feature. And in the classical setting, we would be interested in such controllers. And Bantal, Boyd, and Nemirovsky actually showed that in the very same paper that actually causal controller U can be represented as a linear function of the original output y, if and only if it can be represented as a linear function of the purified outputs eta. Therefore, this means that actually the family of linear output feedback policies, if you were to interested in them, should be also equivalent to the family of linear purified output feedback policies. Okay, so now this was a little bit of background on what do we know about this problem in the classical setting. So now we will see how can we leverage these results. So now I'm going to discuss some structure results for linear quadratic control problem. Okay, to do that, we are looking at this robust control problem, right? And then we take its dual by interchanging the minimization and maximization. Okay, so the primal and robust dual control problems could be seen as versions of zero-sum games, right? So in the primal problem, the min player plays first and the max player sees its strategy and reacts. In the dual problem, the max player moves first and then the min player reacts. So in both cases, the second mover sees the strategy of the opponent and therefore has a leverage. So this means that actually we have immediately this inequality between the optimal value of the primal problem and the optimal value of the dual problem, which we refer to as the weak duality, right? So this is quite perhaps straightforward, right? And now what we're going to do is we're going to build upon this weak duality. So this is going to be the center of the proof, okay? And we're going to establish some structure results. And the structure results that we're going to see in a bit is going to be that the primal problem is solved by a linear policy in the robust version, even though we robustified it. And next, we will see that the dual problem is solved by a Gaussian distribution. And finally, we will see that strong duality actually holds. Okay, so to establish these results, I would like to tell you how do we actually construct a proof for that. So now what we're going to do is we're going to look at this weak duality that we have, right, this inequality. We're going to construct an upper bound to the primal problem and a lower bound to the dual problem. So we're going to see how to construct them. And in the step 3 of this proof, we're going to show that the upper bound and lower bound constructed in steps 1 and 2 actually coincide. Therefore, all the inequalities that we have seen here in this right-hand side of the slide are in fact equalities. And each equality that we see is going to imply a structure result that we have seen before, okay? So let's start with step 1. So now our aim is to construct an upper bound on the primal robust control problem. So we're going to obtain this upper bound by restricting the controller's feasible set to linear policies, okay? And we're going to relax nature feasible set to Galbraith ambiguity set. Therefore, we make the feasible set of minimization problem smaller, the feasible set of the maximization problem larger, and we will see this is going to give us an upper bound, right, immediately because we're going to establish these results through restrictions on the minimization feasible set and then enlarging the feasible set of the max player. So how does this, I would like to discuss a little bit, how does actually this Galbraith ambiguity set that I'm going to define in a bit actually provides a larger ambiguity set. So what we're going to do is we're going to inflate these ambiguity sets W, and in fact, we're going to give more power to the adversary, right? So to see how this is done, let's look at the Piquet distribution of the initial state x0 from within the Wasserstein ball Wx0. So by construction, the two Wasserstein distance of these distributions from the nominal Gaussian distribution at the center of the ball is no larger than the radius of the ball, right? Which is Rx0. And remember that both of these distributions have zero mean, right? We have seen in the beginning of this presentation that Galbraith's corollary tells us that two Wasserstein distance between two distributions with zero mean is bounded below by the Galbraith distance between the distribution's covariance matrices. That we call it Galbraith distance G, right? And now we can define a Galbraith ambiguity set, actually, which effectively contains all distributions of the initial state x0 that satisfy these two properties. First, every distribution in the Galbraith ambiguity set must have zero mean, right? Second, Galbraith distance of this distribution covariance matrix from the nominal covariance matrix must be smaller than or equal to the radius of the original Wasserstein ball. By Galbraith's inequality, then every distribution in Wasserstein ambiguity set also belongs to the Galbraith ambiguity set. Therefore, the red Wasserstein ambiguity set must be a subset of the yellow Galbraith ambiguity set that we've seen here before, here in this presentation. Okay. So now we can do that actually for all measurement noise terms, right? And when we combine all of these individual Galbraith ambiguity sets to a joint Galbraith ambiguity set, script G, such that all exogenous terms are mutually independent under every distribution in G, we actually provide a larger ambiguity set for the adversary effectively. Therefore, our upper bound problem is in this form, where we look at the minimization problem is concentrated on the controllers that are linear. And the max player is only looking at the distributions that falls into this Galvig ambiguity set. Through a very simple computation, we can actually show that this problem, the min-max problem that we see here, is equivalent to a finite dimensional min-max problem. And this can be seen as follows. So the states are linear in the inputs. The inputs are restricted to be linear in the purified outputs, and the purified outputs are linear in exogenous uncertainties. Therefore, the states and inputs are linear in the process noise W and the measurement noise V. And the cost function is quadratic in W and V, therefore, and which implies that the expected value only depends on the underlying covariance matrices of W and V. Now, in the following, we denote the covariance matrices of W and V by capital W and capital V, respectively, and these are just large block diagonal matrices, okay, as indicated in these ambiguity sets. And each block corresponds to a particular time period. And finally, the requirement that P belongs to Galvig ambiguity set is then equivalent to requirement that the underlying Royce covariance matrices satisfy their respective Galvig constraints with the same radiuses as these original ambiguity sets. Okay. Okay, so now let's see how we actually construct a dual problem, lower bound on the dual problem. So this was step one. Now the step two is just that we look at the dual where we interchange max and the min. And now our aim is to provide a lower bound to this problem, right? And it's going to be achieved very, very simply in a simple form. So we're going to restrict the feasible set of the nature's problem to contain only normal distributions that falls into the same ambiguity set W. Therefore, let's call this ambiguity sets as WN, which are the normal distributions that falls into this ambiguity set script W. So that this is effectively a lower bound, right? Because we just restrict the maximization problem's feasible set. So now this outer maximization problem only contains normal distributions. What happens is that, well, the inner problem is a classical linear quadratic Gaussian control problem. So I mean, we know how does the optimal controller looks like. We know that it's actually linear in the purified outputs. Therefore, without loss of optimality, what we do is actually we restrict this inner problems feasible set to linear controllers in the purified outputs without loss of optimality. So basically, our lower bound problems looks like that, right? So it is achieved by just restricting feasible set of the max player. And without loss of optimality, we managed to also restrict the min player's feasible set. So then we show that through a very simple manipulation, that in parallel to what we have seen in step one, that this lower bounding problem, lower bar D star, also is equivalent to a finite dimensional max min problem. So as in step one, the linearity of control inputs in the purified outputs implies that the expected cost depends on only on the covariance matrices capital W and capital V. And the fact that the two Wasserstein distance, optimal transport distance between two normal distributions coincide with the Galvig distance between their matrices is indicated by these ambiguity sets GW and GB. Therefore, the fact that when we ask a distribution P to belong to this script WN is equivalent to asking that these underlying noise covariance matrices satisfy their respective Galvig inequalities. Okay, so now this is step two, right? And now what we can actually do is we can put them together, right? So actually our upper bound problem is reformulated in this form. Our lower bound problem actually reformulated in this form, we just seen it. These problems are very similar, right? So the only difference seems like the objective values are the same, but the order of the minimization maximization is different. Well, then what we can actually do is, thanks to all the classical min-max results that is in the literature, we show that this objective problem is convex in Q and U, and is linear in the covariance matrices W and V. The feasible sets of the minimization problem where Q and U is convex, While the feasible set of the maximization problem over covariance matrices W and V is convex and bounded, well, we can establish by using the celebrated Sion's min-max theorem that the optimal value of this lower bound problem should be equivalent to the optimal value of the upper bound problem. Therefore, order of minimization and maximization between these two problems actually does not matter. This effectively tells us that, well, if the upper bound problem and the lower bound problem that we have in these inequalities are equivalent, this means that all of these inequalities that we see in the slide are in fact equalities. This means that we have these equalities, but each equality means that we can establish some type of a structure results because these were crafted in a very particular way. So, but equality A tells us that the problem is solved by linear policies because upper bound problem was established by linear controllers, right? Equality B tells us that the dual problem is solved by a Gaussian distribution that says that even though we contained non-Gaussian distributions in that problem, the worst case distribution is attained by a Gaussian distribution. And equality C that we see here tells us that the strong duality holds. Okay, this is very nice. So let's see if we can actually use these results to see if we can actually design some efficient algorithms to solve this problem if we were to implement it. So now what we're gonna be, this brings us to the last chapter of this presentation where we will see if we can actually leverage these results to design some algorithms. Okay. Okay, so thanks to the reformulations that we have seen before, right? These gigantic forms also with their, we also seen how does these actually sets GW and GV looks like. What we can actually do is we can dualize this inner problem, inner maximization problem, and we can reformulate this problem as an entire, this min-max problem as a huge semi-definite program, where the number of decision variables of this STP scales with the time horizon t and with the squared state dimension. Okay, so so from theoretical point of view, this is great news, right? So we made these reformulations. It means that our distribution robust linear quadratic Gaussian control problem is actually tractable. And it can be solved in polynomial time. But from practical point of view, this is not really satisfactory because large STPs are very difficult to solve. Therefore, we need to, if you want to really use this, we would like to maybe perhaps find a different solution method, right? Okay. So now let's look at the primal and then dual problems again. What we know is that because we saw that the strong duality holds, actually this primal and dual solutions form a Nash equilibrium. Therefore, if we could get P star that solves the dual problem, then we could compute optimal inputs U star very effectively because we know that this problem is a linear quadratic Gaussian control problem, that P star is a Gaussian distribution. We can just solve it by using dynamic programming and Kalman filtering. Now the question is like, how do we get P star then, perhaps, right? What we do is we're going to look at the dual problem, okay, which is in this form. It's a max-min problem. This is the reformulation. And simply call this inner problem as a function f as a function of the covariances, the block covariances W and V. So we can show that this f is concave and smooth. Well, what we can actually do is we turn this whole large problem into optimization of our covariances. And every time that we fix the distribution, the inner problem is in fact a classical linear quadratic Gaussian control problem that we know how to solve. Now the question is like, can we actually solve this maximization of function f effectively? Because f is concave and smooth, yes, we can. So we can actually use Frank-Wolf algorithm to solve this optimization problem where we maximize over W and V and of this function f. And then Frank-Wolf algorithm, let me quickly show how it actually works, is that, so at each iteration of this algorithm, we have two steps. So in the first step, we construct the first order Taylor approximation of the objective function f around the current iterate that we are having, W and V. And then we solve a direction finding subproblem, which maximizes this first order Taylor approximation over the original feasible set. And in step 2, we construct a new iterate, which is obtained by moving from previous iterate towards the solution of the direction finding subproblem by a step size alpha. Okay, so this is the Frank-Wolf algorithm in the most general form. And we basically, what we should do, if we can solve also these problems, is that we should just iterate. And if alpha is inversely proportional to the iteration number, then we know that the Frank-Wolf algorithm is guaranteed to find an epsilon optimal solution of the nature's problem in 1 over epsilon iterations. Now, as you see, actually, this problem is very nice, but we need to compute these gradients, right? So, and we need to solve also these sub-problems, right? Which are indicated in the step 1 here. Okay. Okay. So basically, this means that this Frank-Wolf algorithm that we just designed is as fast as it can get, and its limitation as we make this direction finding subproblems efficient, right? So this is the bottleneck of this actually algorithm that we have seen before. But we see that this is actually the case. This is going to be the case that we can solve this problem very effectively, because this F actually is optimal value of a classical linear quadratic Gaussian control problem, right? When we fix the W and V. And from linear quadratic control, classical linear quadratic Gaussian control theory, we know that F actually constitutes a weighted sum of several functions that are defined recursively through Kalman filtering, okay? Therefore, F is actually really similar to that of a neural network. And we can actually take its gradients by using automatic differentiation and backpropagation. Well, these are particle gradients. So actually what we did in the end is that we use Pymanops with PyTorch backend propagation to compute these gradients. Okay. So, okay, these gradients are given, but we still need to solve this optimization problem, right? We use this PyTorch automatic gradient tool, but we still need to solve these problems. But we can actually see that this problem actually also separates over time, right? Because of this particular nature of these W's and V's being block diagonals. Therefore, actually, we can also show that this direction finding subproblems also decompose into 2t plus 1 small STPs. And these STPs actually, in fact, can be solved in parallel, which we do. And we can actually take the duals of these each particular STPs, show that strong duality holds, and we can actually solve them by fast bisection method, which is going to be just an optimization over just one variable that's actually in fact going to turn out to be bounded. Okay, so we implemented all of these, and we show that so we actually compare this method that I just described to Mossack if it were to just solve this large STP. Okay, so this plot actually shows the average run times as a function of the time horizon for randomly generated problem instances with 10 inputs, 10 outputs, and 10 states. And what we see here is that Frank-Wolf actually provides us a 600-fold speed up. And well, we have some other experiments as well. And then if you're interested, you might go and check it. And okay, so this brings me to the summary of my results that our results that I just shared. So I would like to actually talk very briefly about the extensions that we have, okay? Because one might think that, okay, maybe these are really like particular cases that we were looking at, and that's why we get these results. It turns out not the case. So all the things that we can do in the classical linear quadratic Gaussian control setting should follow through if we could actually construct the ambiguity set in a particular way. Meaning that because we know that the classical linear quadratic Gaussian control problem still tractable when we have elliptical distributions, we can actually change the center of the balls, these ambiguity sets, to be elliptical disturbance distributions and still get the same results. And this is particularly perhaps interesting because Gerbich's ambiguity, the lower bound that we have seen, also holds for elliptical distributions, so not only for Gaussian distributions. Well, should we only consider optimal transport Bayes or Wasserstein ambiguity set? No, we also show that we can actually use Kullback-Leibler type of divergences to define these ambiguity sets. and our results would still go through. And so we also showed that we can actually use a couple of other divergences as well. And we can also relax this non-zero mean assumption that all the distributions actually have a zero mean. And we show that if the nominal distributions have mean zero, then the worst case distribution is also attaining a mean zero. So this actually turns out to be without loss of generality if we consider zero mean distributions in the center. And well, finally, we show that our results also could extend to infinite horizon setting when we are looking at an time average cost. And for that, we need to put some more assumptions on the system that we're looking at. So we want the system to be stabilizable and detectable to show that we can actually still establish the structure results. Okay. Well, this brings me to the end of my talk. So thank you very much for your attention, and I will be very happy to answer it if you have any questions.